Okay, good morning, everyone. So in the last lectures, we consider the stiffness of the ODE. So remember, an equation is stiff if you have to reduce the step size to a very, very small number. So then you can solve it without, creating instability. So one particular test equation is when you have y prime equal lambda y, okay, and you try to see whether your method is stable or not. So we consider the Euler method and implicit Euler method, and you can write down yn as a polynomial q to the power n of y0. So we want the absolute value of q h lambda is less than 1. Okay, so remember lambda is the right hand side here. It's just some number that can have a negative real part is very large. Okay, so then we define the region of absolute stability is on the complex number, so that modulus of qz is less than 1. Okay, and last time we consider the Euler method. Yeah, so the Euler method, if you write down, let me remind you how to write out this. Yeah, so if you have an Euler method, then so remember by now you should know Euler method is given by this formula, right? So yn is just yn minus 1 plus h f dn minus 1 yn minus 1. Yeah, so in our case you have y prime equal lambda y. Okay, so this one is your f, right? So then you have yn is yn minus 1 plus h, and now instead of f you write lambda yn minus 1. Yeah, and so this one is reduced to 1 plus lambda h yn, sorry, yn minus 1. Yeah, so then I label this one is q of lambda h, okay, yn minus 1, and then you can relabel the yqz. Okay, so the qz is just 1 plus z. Yeah, and then we want to find the region so that z in the complex plane, so that the modulus of qz is less than 1. Okay, and that is exactly what we have here. So if you go back to the slide, you see this is a 1 plus z less than 1, and if you write down the complex plane, then this one is just a circle. Well, I mean inside the circle, right? Center at x equal minus 1 and y equals 0, radius 1. Yeah, so that is explicit Euler method. So how about implicit Euler method? So implicit Euler method is, so you have, so implicit Euler method, you have, well, implicit Euler method, the other name is just the trapezoidal method. Yeah, so now, so for the trapezoidal method, yn plus 1. Yeah, okay, now I use yn plus 1. It's just yn plus h and the trapezoidal rule, so f of dn yn plus f of dn plus 1 yn plus 1, right? So remember, this is the area under the trapezium that have Tn and Tn plus 1 in the base. Yeah. And now, so remember your equation is just y prime equal lambda y. So then I can write yn plus 1 is yn plus h lambda yn plus h over 2, yeah, plus lambda yn plus 1. Okay. And now I can rearrange it. So now yn plus 1, I just move it to the left. So I got h lambda over 2 yn plus 1 equal 1 plus h lambda over 2 yn. Okay, and then I have yn plus 1 is just 1 plus h lambda over 2 over 1 minus h lambda over 2 yn. Okay, so now if I label this one, the h lambda is z. Yeah, so label this one is z. Then my qz is just equal. So this one will be, so this one is of the form maybe yn plus 1, yeah, is of the form 1 plus z over 2 over 1 minus z over 2 yn. Okay, and this one is my qn. And that is exactly on the slide, yeah. So if you go back to the slide, then then you see the qz is just 1 plus z over 2, 1 minus z over 2, and the region of stability is just, you know, the modulus of this one less than 1. And last time we showed that, you know, I mean, this one you can write down is the region on the half plane. Okay. And now what happens if I have a more complicated method like explicit Ronch-Cutter method? Then what is the region? Well, before the region, what is the qz? Okay, so the qz, the claim is 1 plus z squared over 2, z cubed over 6, z 4 over 24. So how do we get this q? Okay, so now remember the Ronch-Cutter method of order 4. So by now you're familiar with this method, yeah? So now if I write down the formula, then I should have psi 1, yeah? Psi 1 is yn plus, and if you remember the table, so it will be, well, maybe let me write down the table again, yeah? So we just copy out the table again. So 1/2, 1/2, 1 here, 1 over 6, 1 over 3, 1 over 3, 1 over 6. Okay. So remember, first you have to write out psi 1. Okay, is f of Tn. No, sorry, psi 1 is just yn, yeah. So psi 1 is just yn, yeah. And then psi 2 is just yn plus h over 2 f of Tn psi 1. Okay. But now remember, what is your f? So remember, we consider the y prime equal lambda y. Okay, so this is the ODE we are considering. Then this one will become 1. So this one will become yn plus lambda psi 1. Okay, because now the parameters, the second parameter is psi 1. So you have to put in lambda psi 1 h over 2, right? Yeah. And then what is psi 1? Well, psi 1 is just yn. So actually you can reduce this a bit more. Yeah. So yn is, sorry, this h lambda psi 1 is just yn. Yeah. So then then you can combine it. So it's become 1 plus z over 2 yn. And remember, z is h lambda. Okay, so that is xi2. And what is my xi3? So xi3, so remember we have yn. So in this case, yn plus h over 2 f of Tn plus h over 2 xi2, right? Because you have 0 here. Yeah, so you have 0 here. So then I have to replace f by lambda xi2, right? So I got yn plus h over 2 lambda xi2. Okay, but remember, what is xi2? So xi2 is right here. So we work it out. Xi2 is here. So you put it in. So yn plus. So remember, we replace this one by z over 2. Yeah. So h lambda is just z. So z over 2. And what is xi2? So xi2 is just 1 plus z over 2. So 1 plus z over 2 yn. Okay. So this is xi2. Yeah. And now what is the result? So now you expand it out. Yeah. So you got yn plus z over 2 yn plus z squared over 4 yn. Okay, so you got 1 plus z over 2 plus z over 4 yn. So this is your xi3. Okay, so the whole sequence here. And then the last one will be xi4. So what is xi4? So xi4 will be yn plus, okay, so you don't have anything for xi1, nothing for xi2, but something for xi3. So f Tn plus 1/2 h xi3. And then you replace this one by lambda xi3, yeah, yn plus h lambda xi3. And now, you know, I mean, you put it in. So this one is z, yeah, so h lambda just z, and xi3 is the one that you have before, remember? So this one is your xi3. So then you got 1 plus z over 2 plus z squared over 4 yn, yeah. Okay, this is my xi3, yeah. And now I expand it out. Okay, so I know that yn now is a common term, so I just put yn to be the front here, and I have 1 here, yeah, for this one, plus z squared over 2 plus z cubed over 4. Okay, so because you expand it out, right? So this one gives you z, this one is z squared over 2, z cubed over 4. Okay, and so this one is xi4. So now what is the last term? So the last term will be yn plus 1, right? Because now you finish. Remember, in RK4 you have only to complete up to xi4. Okay, and now you put in your formula for yn plus 1. So yn plus 1 is, remember, not just yn plus h over 6 f of Tn xi1 plus h over 3 f of Tn plus h over 2 xi2 plus h over 3 f of Tn plus h over 2 xi3 plus h over 6 f Tn plus h. So remember, C4 just h, okay, xi4. But now remember, your f is just lambda y, yeah. So then this one will reduce to yn plus lambda h over 6 xi1 plus lambda h over 3 xi2, okay, plus lambda h over 3 xi3 and plus lambda h over 6 xi4. And remember, you have on the xi1, xi3, xi1, xi2, xi3, xi4 already, you know, expanded in the z form. Yeah. So go back to this. So this is z over 6. Yeah. And what is xi1? So xi1 will be, so you go back to the beginning. So your xi1 is here. So xi1 is just yn. Okay. Then what is your xi2? So this one z over 3. So what is xi2? So xi2 is right here. Yeah. So 1 plus z over 2 yn. So 1 plus z over 2 yn. Okay. And then what is xi3? So xi3 is, so before xi3 you have to have z over 3. And then xi3 is just 1 plus z over 2 plus z squared over 4 yn. Okay, it's a bit tedious, but at the end of the day, you will see the results will reduce to something very simple. So the last one is just z over 6 xi4, and xi4 is 1 plus z squared over 2 plus z cubed over 4 yn. Okay, so now we collect the terms. So you know yn will be the common terms. Yeah. Okay, and now what is the term for constant? So you have 1, okay, and here you have 1 over 6. No, sorry. So no more constant, right? So this one is, z. Okay, so no more constant. So how about the term for z? So how about the term for z? So you got 1 over 6 here, and you got 1 over 3 here. You got 1 over 3 here. You got 1 over 6. Okay. So that is for z, yeah. And what is z square? Well, z square you have right here. So this one z square. So you got 1 over 6. Okay. So this one gives you z square, yeah. This one gives you z square as well. So 1 over 6 plus 1 over 6. Okay. Plus z cubed. Okay. So how do you get the z cubed? So z cubed is again, you look back at the terms, yeah. So there's no z cubed here. So z cubed is here. So 1 over 12. So 1 over 12 plus yeah, 1 over 12 here, and this one give you 1 over 12. So 1 over 12 for z cubed, yeah. And the last one is z to the 4. So z to the 4 is, you just have 1 over 24. Okay. So now when you sum it up, then you got yn. Well, you got yn and then 1, yeah, plus, so this one 1 6, what plus 1 6 is 2 over 6 is 1/3, 1/3, 1/3, 1/3, so just 1. Okay. And 1 6, 3 over 6, so just z squared over 2. Okay. And this one is just 2 over 12 is z cubed over 6. Okay, and the last one is z4 to the 24. So this one is your QZ. Okay, So if you go back to the slide, then this is exactly what we have in the slide. Okay. So that is the one we have here. So 1 plus z squared over 2 z cubed over 6 and z4 over 24. Okay. And now for implicit Runge-Kutta method of order 3, you can show that QZ is, of this form. Yeah. So you have to do some calculation here. And then now if you go to implicit Runge-Kutta method of order 4, then QZ will take this form. Yeah. Okay. And now, so I mean, if you try to find out the region where Z of the point Z, so that the modulus of QZ less than 1, then it's a bit complicated, but essentially for explicit, then you see that the region of stability is a very small region. But the implicit Runge-Kutta method of order 3, you see the region of stability is very big. The black one, can extend to infinity, and only the white is not stable. Okay. And now, so remember in MATLAB, you have a few ODE solvers. So in the project, you saw the ODE 45. Yeah. So ODE 45 is just one solver in the family. So you have ODE 45 that use Runge-Kutta method of order 4 and order 5. Okay, but you can have ODE 23. So it use Runge-Kutta method of order 2 and order 3. Yeah, and there is ODE 113. So it use Adams Bradford method. Yeah, and ODE 15S for solving a stiff equation. So BDF is backward differentiation. So we don't study this. Yeah, and we don't study this Rosenbrock. And for ODE 23, they just use trapezoidal method. Okay, so the order is just order 2, and so this one is backward differentiation, and so on. So we just use ODE 45 in the project. Yeah, we just use Runge-Kutta method of order 4 and order 5, and this gives you like a good accuracy already. And so how do you use ODE 45? So remember, you have to give the function as anonymous function. Okay, so the function should depend on t and y, and you give the t span, you give the initial condition, you give the option. So you cover this. We cover this in the project already. Yeah. And then you have to put in, the initial condition, and then you just code it. So you can set the option as well. So this one, relative tolerance, absolute tolerance, and you've seen that. Yeah. And then the output. Okay, so the output will be an array. Yeah. And you've seen that in the project already. So that's about it. So now you want me to go back to the topics of QZ or not? So because example 26 is one of the past exam question. So you want me to cover this question? Okay, so maybe we do this. Yeah, so this one is exam question in 2019. Yeah, so how do we show that QZ for IRK3 is given by this polynomial? Well, so now go back to this table. So if you let me share the screen. Yeah, sorry, a piece of paper. So now you have a table like this. You have a table. Question. Sorry, what is the question? A-stable method, does it have to cover the whole left plane? Yes, it has to cover the whole left plane. Yeah, so that's a definition. Okay. Okay, but now go back to the implicit Runs-Kutta method order 3. Yeah. So now you have a table like this. So 0 to third, 1/4 minus 1/4, 1/4, 5/12, 1/4, 3/4. Okay, so this one is IRK 4. No, sorry, IRK 3. Yeah. And now how do we figure out the QZ? So remember, first you have to write out what is Xi1. So Xi1 will be Euler method is not A-stable, yes. But implicit Euler method is A-stable. So we discussed that last time, yeah. Okay, so now go back to this example. So Xi1, will be Yn plus f of Tn. Well, maybe you have to multiply h/4 outside first, yeah. Xi1, okay, plus or minus h/4 f of Tn plus 2h/3 Xi2, okay. And then you have Xi2 is Yn plus h/4 f Tn Xi1, yeah, plus 5h/12 f Tn plus 2h/3 Xi2. Okay, so this is your method. And Yn plus 1 is Yn plus h/4 f of Tn Xi1 plus 3h/4 f Tn plus 2h/3 Xi2. Okay, so now we have to plug it in. So remember, our ODE is just y prime equal lambda y. Yeah, so this one is a special ODE to test whether the method is stiff or not. So now we have to replace it into everywhere we have an f here. So then you get a new system, yeah. So you got a new system. So you got Xi1 will be Yn plus h/4 lambda Xi1 minus h/4 lambda Xi2. And you got Xi2 is Yn plus lambda Xi1/4 plus 5, forget the h here, 5h/12 lambda Xi2. Okay, so now you have a system, but this system is linear. Okay, so it's not non-linear, so you don't have to use F-solve here. You can solve it. So there's many ways to solve it. Okay, so but suppose I want to solve it by a linear system. And first I have to rearrange it. So I rearrange it by putting Xi1, Xi2 in the same on the left hand side. So it will be 1 minus z/4 Xi1 So remember Z is just H lambda, right? Yeah. Then I move to the Z1 to the left here. Then I got plus Z over 4 Z2 equal Yn. Yeah, you can rearrange it. Yeah. And then similarly, I can do the same here. So I got minus Z over 4 Z1 plus 1 minus 5Z over 12 Z2 equal Yn. Okay, so make sure that your calculation is correct. Yeah. But then I can write this one down as a matrix. Yeah. So this one is a matrix. 1 minus Z over 4. This one is Z over 4 minus Z over 4. 1 minus 5Z over 12. So you can solve by many methods, but at least one method is good enough. Yeah. So Xi1, Xi2 is Yn. Okay, so this one I call it a matrix A. Okay, so then you just have Xi1, Xi2, just A inverse of Yn. Yeah. So now suppose I try to compute the A inverse. So first step is I try to compute the determinant. So determinant of A will be 1 minus Z over 4, 1 minus 5Z over 12, and minus become a plus Z squared over 16. Okay. So make sure everything is correct. So you got 1 here, and you got 5 Z squared over 48. Okay. And then you got minus a quarter minus 5 over 12. So it will be like multiplied by 3. So this one is 3. So minus 8 over 12. So it will be minus 2 over 3. So minus 2 over 2Z over 3. Okay, just check the calculation. Okay, so this is what I got. Okay, so I got 1 minus 2Z over 3. And so this one is you multiply by 3, then you got 3 over 48. So you got 8 over 48. Yeah. So 8 over 48, then so 48 divided by 8 is 6. Yeah. So you got Z squared over 6. Okay, so check. Okay, so 5 over 48 plus 3 over 48 is 8 over 48. Yeah. And you simplify by 8, you got the square over 6. Okay. Agree, yeah? You still there, yeah? Okay. So my calculation is correct, yeah? Okay, so now what is the A inverse? So if you remember the formula, then suppose you have A is ABCD, yeah? ABCD. Then A inverse is 1 over determinant of A. And then you have to swap B and A. And then this one become minus B minus C. Okay, so this is a formula for 2 by 2 matrix. Yeah, when you try to take the inverse. So now we have our matrix. So now our matrix So this one is maybe like a bar or something like general matrix. Our matrix we have it already. So now our matrix is right here. Okay, so then I just write out A inverse. So if I write out A inverse, then I have, so 1 over the determinant, yeah? So 1 over determinant is just 1 over 1 minus 2z over 3 plus z squared over 6. So this is my determinant. And I just need to swap a diagonal. So I have 1 minus 5z over 12, 1 minus z over 4. And then I swap the sign. So I swap the sign and minus z over 4 and z over 4. Okay. So now what is xi1, xi2? So xi1, xi2 will be A inverse of yn, yn. Okay, so now you have to, well, what is just yn and then the vector 1, 1, yeah? So then it will be 1 over determinant of A again, yeah, okay. So I just, and then you have to put in the matrix, so 1 minus 5z over 12, z over 4 minus z over 4, 1 minus z over 4, yn, yn. So it will be, essentially you have to take this, you plus this, yeah? So take this, you plus this, multiply by yn, so you take yn outside. So it will be yn, okay? So for the first one, yeah, so yn will be, you take 1 minus 5z over 12 minus z over 4. Okay, so this one gives you xi1. So hopefully our calculation is correct, yeah. And then we'll have to divide it by the determinant of A, yeah. And then the second one will be yn z over 4 plus 1 minus z over 4 divided by the determinant of A. Is it correct? So far still correct, right? Yeah. Why no clue? This one is just 2 by 2. 2 by 2 linear system. Well, I mean symbolic, right? I mean this is just a symbolic calculation. But I mean it's just a 2 by 2 linear system. So you should know how to do it. Okay, that's fine. Then you just do it like, I mean, when you have time, you can redo it, okay? But then what I have is, you know, the first one will be, well, essentially my claim is xi1 will be, so this one is xi1, yeah, and xi2. Okay, so the xi1 will be just, so 1 minus 5z minus z over 4 divided by the determinant. I can write down, yeah. But this one is like, so you multiply by 3, so 1 minus, so 3 multiplied by 4 is 12, so 3. So AZ over 12, yeah, yn, yeah, divided by 1 minus 2z over 3 plus z squared over 6. Okay, agree? Yeah, these are determinant. And then the second one, the y, the xi, 2, it's just yn, and this one cancel with this one, so you just have only 1 divided by the determinant 2z over 3 plus z squared over 6. So you solve it. So you solve your linear system, right? So now you don't have xi1, xi2 anymore. Okay, so remember we have the linear system in the beginning, yeah. Okay, so this one is a linear system you got from the implicit method. And you see in your project you use fsolve, but then because you have a very complicated ODE, yeah, but in this case the ODE is just a linear lambda y, so it's become a system of two linear equations, and you can solve it. So you can solve it by whatever methods you prefer. Okay, substitution. So in my case I just use a matrix, yeah. And then after this step, then you got xi1, xi2. Okay, so there's no xi1, xi2 anymore. So everything just in terms of yn. Okay, and now you plug it in. You plug it in the final equation. Yeah, because now you got xi1 and xi2. Okay, so now we try it. So now yn plus 1. Okay, so we do the last step, yeah. So yn plus 1 will be yn plus h over 4 lambda xi1 plus 3h over 4 lambda xi2, right? And now we have xi1 and xi2 already in terms of z and in terms of y. So now this one is just z over 4, yeah. And now I put in my xi1. So my xi1 is just yn 1 minus az over 12. Okay. And I divide it by 1 minus 2z over 3 plus z squared over 6. Okay, this is my xi1. And then plus, so 3z over 4 by xi2. So xi2 is yn divided by 1 over 2z over 3 plus z squared over 6. Okay, so now I need to simplify it. Okay, so now you see everything now just in terms of z and yn, and now I want to simplify it to see what happened. Okay, so now if I simplify it, then let's see whether we get the correct results. Okay, so this is a bit tricky. So we got yn plus 1 is, okay, so now I can take our yn to be the common terms, yeah. Okay, so yn is just a big, now I have a big bracket. So for yn, yeah, because you can see that yn is everywhere here. Okay, so yn is common term. And now what I have left is just 1 plus, okay, so look carefully, so z over 4, 1 minus az over 12 divided by 1 minus 2z over 3 plus z squared over 6 plus 3z over 4. Okay, and multiply by 1 divided by a common denominators here, so z squared over 6. Okay, so now see, we simplify this and whether we get the qz. So this one is the qz already. Okay, but now need to simplify it a little bit. So now if I simplify it, so very carefully, so I put a big bracket here, then I got 1 minus 2z over 3 plus z squared over 6. So I have to have 1 minus 2z over 3 plus square over 6 plus z over 4 minus, so this one is, so you have a cancellation here. So 2 I divide by 4 is 2, right? So 2 over 12 is just 1 over 6. So you got z squared over 6. Okay, and then this term is just 3/4 of z. Well, so it seems that we got something, right? So now z squared over 6 got cancelled. Z squared over 6 got cancelled. Yeah. And now what is the remaining? So remaining is just, so you just got so this one is 1/4, 3/4, just 1. And 1 minus 2/3 is just 1/3. So you just got 1 minus z over 3. That's it, right? And then 1 minus 2z over 3 z squared over 6. Okay, so this is the Q set. Okay, so see whether we get it correctly or not. So now if I go back to the slide, then no. So this one is 1/4 plus 3/4 is 1. So 1 minus 2/3 is plus 1/3, not minus. Okay. So far so good, right? Yeah. Okay, so now we go back to the slide and see whether we get the correct answer. So yes, so we get the correct answer. Okay. So we are lucky. Okay, so we get the correct answer. So, but you see, I mean, it can be done. I mean, it's not hard. It's just a bit like tedious. Yeah. Yeah, it's true. I mean, it's true. So there's a lot of calculation, but you know, I mean, this it was exam question 2 years ago. Okay. Yeah. So any questions? So that seems that. So this one you can do it. Okay. So the same principle. So let me stop the recording.